Okay, thank you, Chairman. And I want to first thank the organizers for this opportunity to present this voice. So, yeah, I will talk about orbital dynamics in. Sorry. The orbital dynamics in centrosymmetric system, and this is what I will do. Let me remove this.
Three dots. Three dots. Five.
So 여기 더 보이는 거. I can understand. Yeah. No. Oh.
Yeah.
So I shouldn't touch this.
Okay, so this is what I will talk about. Basically, I was asked to have tutorial and have seminar, and this is what I will.
So now it is not working properly. Yeah, it is coming back and.
Can you click the mouse and the arrow?
Yeah, that does not work somehow. You have to first click the screen. Okay. Mouse. Yeah. Okay.
So this is what I will talk about. In the tutorial part, I will first illustrate that orbital angular momentum is not necessarily quenched in solid. And in the second part, I will try to discuss some experimental implication of this fact. So that is the tutorial part. And in part 3, I will discuss some orbital dynamics. Well, it has many things in common with the spin dynamics, but some properties are very positively different from spin dynamics. So I will discuss this difference. Okay, so first part, orbital angular momentum not quenched in solid. So I will start with a simple discussion about spin Hall effect. So when an electric field is applied from, we have an external electric field, electron may exhibit spin-dependent sideways motion. So that is the spin Hall effect. And we know that it is very useful for electrical control of magnetism. And okay, so here I copied graphs from Hyun-Woo's their insightful theory paper in 2004 that illustrates the mechanism of intrinsic spin Hall effect in non-centrosymmetric system. In non-centrosymmetric system, we know that crystal momentum can couple to electron spin. And this coupling generates momentum-dependent spin direction, which I may call spin texture. Now, in this, in the presence of a spin texture, suppose we apply electric field. Then Hyun-Woo has demonstrated that the electron acquires a spin component that is originally absent in equilibrium. And additionally, generate a spin component, generate the spin fulcrum. So in this mechanism, spin texture is crucial to have a spin Hall effect. And spin texture comes from the spin momentum coupling, and we know that in this kind of coupling is possible only in non-centrosymmetric system. That means this mechanism does not work in centrosymmetric systems. But according to experimentalists, many materials that have been examined in the context of the spin Hall effect are centrosymmetric. So here, red-colored materials are centrosymmetric. So probably we need to understand how a spin Hall effect can arise in centrosymmetric system and what are the roles of a spin coupling in those cases. Actually, this paper by Murakami, Nakaosa, and Chang in 2003, they addressed the spin transport in gallium arsenide and indium antimony. They are both non-centrosymmetric system. Nevertheless, the model Hamiltonian is actually centrosymmetric. And so from this centrosymmetric Hamiltonian, they demonstrate the spin Hall effect. And one strange thing is that here, the spin is not a real spin, but it is the combination of orbital degree of freedom and spin degree of freedom. And so maybe we can ask, what is the role of the orbital or spin-Hall effect here? And what is the role of the spin-orbit coupling in this material? So to answer those kind of fundamental questions, it is sometimes useful to think in terms of fundamental Hamiltonian. So suppose I have an array of atoms, and maybe we can take these three terms as a fundamental Hamiltonian: kinetic energy, potential energy from the crystal, and this is a spin-orbit coupling, fundamental spin-orbit coupling. Now, if we turn on electric field from outside, we will have an electrostatic potential correction. So that will be added to this term here, this potential energy term. And since this potential energy term appears here as well, we will have this additional spin-orbit coupling. But this additional coupling is very, very, very tiny because electrostatic energy scale is, at best order of 1 electron volt, whereas here we have a mc squared, which is order of 1 mega electron volt. So this correction to spin-orbit coupling is usually ignored. Then we have to deal with this spin-orbit coupling to understand spin-Hall effect. And for this original spin-orbit coupling, it is well known that this term is sizable only very close to the nucleus. Then we may make a kind of atom center approximation. Then this term may be replaced by a very simple and famous term as L. So here L is something like maybe we can take it as some new internal degree of freedom electron. And this is my fundamental Hamiltonian in the presence of electric field. Now you can see that spin appears only here and it couples only with the orbital angular momentum. So if something interesting happens to spin, that means it should be mediated by orbital angular momentum. So if we want to generate some interesting spin response from the electric field, it should be somehow connected to spin degree of freedom. And for connection, well, we know that electric field is connected to crystal momentum. And we see that spin is connected to orbital angular momentum. Now, to make a connection between electric field and spin, we need a connection between crystal momentum and orbital angular momentum. Without it, electric field can generate spin response. So here, S dot L basically generates some correlation between orbital and spin degree of freedom. And so in this picture, we can now see that if something happens from a spin, actually it should be inherited from the properties of orbital angular momentum. So in that sense, we may even say that orbital dynamics is more fundamental than spin dynamics. And this viewpoint was actually emphasized by these two papers, Tanaka et al., Kontani et al. They examined intrinsic spin-Hall effect in 4D and 5D transition metals, and they calculated spin-Hall effect for various 4D and 5D transition metals. And they said that intrinsic spin-Hall effect in this material is inherited from gigantic intrinsic spin-Hall effect. So the material has intrinsic tendency to make a sideways motion depending on this orbital degree of freedom. And electron spin simply aligns or anti-aligns itself with respect to orbital angular momentum. And that is interpreted as a spin-Hall effect, or positive sign or sometimes negative sign. Okay, so that said, maybe we need to discuss what is orbital dynamics and what is orbital Hall effect. Or to be precise, maybe I should call it orbital angular momentum Hall effect, because later I want this to certainly a different version of orbital Hall effect. Okay, so here is a cartoon prepared by the chairperson. So suppose we have a certain two-dimensional array of atoms, and these yellow things represent electron. And if we apply electric field, we know that some of the electron will generate Hall motion or a transverse motion. And what I mean by orbital Hall effect is the following. So when electrons make a transverse motion, electrons do not simply propagate, but instead they make a kind of a circling motion. So that means what I mean by orbital angular momentum Hall effect. And this view graph is beautiful, but it is very, not very comfortable, because we've learned from the solid state physics that in solid, out of many possible electron orbitals, only this kind of orbital without orbital angular momentum are realized in equilibrium unless the system has a very strong spin-off coupling. Whereas those kind of complex orbital with orbital angular momentum is kind of forbidden. But this picture actually predicts that out of this equilibrium orbital configuration, they transform to complex orbital when electric field is applied, and that complex orbital generate a spin response through L.X coupling. Yeah. But well, this kind of orbital orbit was not actually addressed by earlier literature. This is a paper by Andrei Brnovik, Taylor Hugh, and Shucheng Chang, published in 2005. They studied p-doped silicon, and silicon has essentially no spin-off coupling, and they calculated orbital Hall effect, and they found that this system exhibits a finite orbital Hall effect without spin-off coupling, and they said that the orbital response could be very fundamental. And actually, this is not the only literature, and you can find many more. Well, if you're really patient with the internet search. So it seems that it is a possibility of orbital dynamics is discovered, forgotten, and rediscovered, and forgotten again somehow. So, and that is probably related to this statement: orbital angular momentum is quenched in solid. So people, I guess, probably did not believe their calculation. And also people did not know how to measure orbital angular momentum dynamics. So here I want to discuss how come orbital degree of freedom can overcome orbital quenching and generate orbital angular momentum dynamics. So to discuss, suppose, okay, let me, neglect electric field. So there is no external electric field. And so crystal momentum is fixed. And for one particular band, suppose its eigenstate has this kind of orbital character, whereas another band, the higher energy, has this orbital character. And suppose somehow, and I will tell you how to prepare this kind of initial state. But suppose we prepare an initial state, which is the superposition of these two orbital wave functions, these wave functions. Then system very naturally generate orbital angular momentum without doing any assistance from outside. Well, and this mechanism is actually exactly same as very famous spin dynamics. Suppose we have certain spin split material, like Rashba coupling material, and suppose for one band, the preferred spin direction is like this one, and for another band of higher energy, preferred spin direction is something like this. And if we prepare some linear superposition of these two spin states, we know that after some time, this spin state evolve and generate this kind of precise spin configuration. And the mechanism is very straightforward. So we may write down the initial configuration as a superposition of two spin eigenstate like this. And after some time, each of the eigenstate components will acquire their own phase vector. And if the phase vector of these two eigenstates are different, we know that the resulting state is a precise spin state. Now, I will do exactly the same thing for orbital configuration. So this is my initial configuration, which is a superposition of this favor state and this favor state. And if I wait just a little bit, each of these eigenstates will acquire a phase vector like this. And this resulting state compared to the original state may be written like this: original state plus some extra, and this extra term has orbital angular momentum. So even without any assistance from outside, the solid itself has a tendency to generate orbital angular momentum on one condition. That is, if we can prepare some superposition of an eigenstate. Then next question is how to prepare some superposition. Well, so suppose we have a certain Fermi surface like this, and for each point on the Fermi surface, suppose the eigenwave function is something like this. So each eigenstate has a p character, but the direction of a p orbital is here it is horizontal, and here it is vertical, and it changes with the momentum. So it is, I may say that this is orbital texture. And we discovered, actually Donald discovered in 2018, that if we apply electric field in this configuration with orbital texture, electron can generate this superposition because, okay, for instance, if suppose I start from here, an initial electron will acquire momentum. And so let's say, so this is the final momentum, but its orbital wave function is different from the eigen wave function. So that means simply by applying electric field to a material with orbital texture, I can generate this kind of configuration where, electron wave function differs from eigenstate wave function. And in this case, this state will evolve to acquire orbital angular momentum. And maybe I can consider another electron down here. And something similar will happen, but this time there is an interesting difference. In this case, this superposition tends to align itself to this equilibrium direction. So it will tend to rotate clockwise. Whereas down here, this superposition state will tend to align itself with this equilibrium, and it tends to rotate counterclockwise. So generated orbital angular momentum direction for this electron with the group velocity, let's say positive, will be opposite to electron, the orbital angular momentum for an electron with the negative group velocity. So here we have positive group velocity upward direction and positive generate orbital angular momentum, and negative group velocity and negative orbital angular momentum generated. And their product, which is orbital current, will add up. And that is the orbital point. And probably you've noticed that all I need is the orbital texture and some mechanism to push momentum. So we may replace electric field by something else, like temperature gradient or whatever that can perturb momentum. So in this sense, I may say that orbital angular momentum dynamics is quite ubiquitous. And compared to this mechanism of intrinsic spinor effect in non-centrosymmetric system, things are exactly the same, except that in orbital case, we can have this momentum spin coupling even for centrosymmetric system. So that's the main difference.
Yeah, this type of questions were here. Yeah, previous one. Could you briefly mention which system you are doing this? As other main questions, this will say, what is the Hamiltonian of the?
Hamiltonian, yeah. Yeah, I didn't write down the Hamiltonian explicitly, and all I assumed is that the system has a momentum-dependent wave function with different orbital character. And regarding the Hamiltonian, I guess I will discuss some that issue later. So I hope you can wait. Yes, sorry. Yeah. If there is no further question, let me move on. Okay, experimental implication. Well, probably the most obvious implication is the generation of intrinsic spin-Hall effect. But in some sense, this is somewhat boring because we've known intrinsic spin-Hall effect for a long time. So this is a kind of reinterpretation or a different interpretation of a or I may say the well-understood intrinsic spin-Hall effect. So Dong and I try to think about something different that can be measurable. So with Sika, try to construct some analog, orbital analog of a spin torque. We know that if the spin current is injected to ferromagnet, we know that that can tilt a magnetization direction. That is the spin torque. So we imagine that maybe something similar may happen if we inject orbital angular momentum to ferromagnet. So without ferromagnet, suppose this is an orbital Hall effect material. If the electric field is applied this way, it will simply generate orbital angular momentum accumulation on one surface and the other surface. Okay? But if we make a contact with a ferromagnet, so probably that orbital angular momentum will be injected to ferromagnet. And if that angular momentum can be delivered to ferromagnet, then we will have a torque. That is what we call orbital torque. So we did a simple model calculation, and we found that both a fielded light torque and damping light torque arise. And depending on material details, this may be bigger and this may be bigger. But anyway, the thing is that orbital angular momentum injection can generate torque. So,
can I very quickly ask? In this case, the injected orbital current interacts initially only with the orbit of the ferromagnet, correct?
Initially, okay, so here in our model, this orbital injected orbital is allowed to interact with the spin of the ferromagnet.
Oh, directly with bicycle.
Yeah. Okay. So here I mean the spin of the coupling of ferromagnet.
Okay, and you also directly interact with the orbit of the ferromagnet, or is this not taken into account?
That is also possible, but we have not taken into account in this particular calculation. And so and we try to estimate how large a spin of coupling is needed to generate orbital torque. So again, we did a model calculation. So here, horizontal axis is the represent the spin of coupling strength in ferromagnet, and vertical axis represent the generate torque strength. And for platinum, we have values somewhere here. And for 3D ferromagnet, we found that the value is somewhere here. So it is smaller than the typical platinum value, but still it is comparable. And if we just imagine a 4D transition metal, although I'm not aware of any 4D transition metal with a ferromagnetism, but if we simply replace the spin of coupling strength in ferromagnet, we found larger torque. So we see that we discovered that orbital Hall effect can generate torque when the resulting orbital current is injected to ferromagnet, and it can be significant. Okay, and now, so mechanism is interesting, but experimentally, we need some ways to distinguish spin contribution to torque versus orbital contributions to the torque. So, and this, okay, so this table summarizes one possible way. In case of a spin torque, we know that most important thing is the spinel effect. And spinel effect sign is determined by heavy metal. So depending on correlation of orbital and angular momentum within the heavy metal, we may have a positive spinel effect or a negative spinel effect, and that generates spin torque of a positive sign or a negative sign. So for spin torque, heavy metal choice is most important one, and ferromagnet choice is relatively irrelevant. But for orbital torque, we inject orbital angular momentum current, and that needs to be converted to spin current through this spin-orbit correlation in ferromagnet. So not only this normal metal choice, but also ferromagnet choices choice matter, because for some ferromagnet, this LS correlation is weak, but for different material, this can be larger. So both normal metal and ferromagnet choices are important for orbital torque. And another factor is that in case of orbital current, well, it is more sensitive to interface quality. So that may affect the magnitude of orbital torque. So I guess Professor Kyung-Jin Lee will discuss this issue, and Dr. Junyoung Kim will discuss this issue in their talk. Now, still another implication, that is orbital accumulation. Okay, so we know this is a very famous question. And one way to detect spin Hall effect is to measure spin accumulation on this side and this side. And exactly that experiment was done by Kato et al. In 2004. And they used Moog to measure accumulating spin on one side and the other side. So this is a very beautiful result. And we may say that this is the most direct detection of a spin Hall effect. Maybe we can try something similar for orbital Hall effect. So can we measure orbital angular momentum accumulation generated by orbital Hall effect? So if we have this kind of orbital Hall effect material, we expect orbital accumulation of one sign here and orbital angular momentum accumulation of opposite sign here. And so probably we need to discuss what is the good material for this study. So we've chosen titanium, so it has a very stable properties. And so this is our band structure calculation, and this is a Fermi surface structure. So basically there are two Fermi surfaces. Well, even though they look very complicated, actually there are only two Fermi surfaces. And each Fermi surfaces have a strong orbital texture and they generate a strong orbital Hall effect. Here for this material, orbital Hall effect, orbital Hall conductivity is estimated to be about 2 orders magnitude larger than spin-Hall conductivity. So probably the orbital Hall effect is more important. And the next question is, what does MOG detect? Okay, MOG is known to detect magnetization, but magnetization can arise from spin moment or from orbital moment. Now, what does MOG detect when we have both a spin and orbit? Well, MOG experiment actually proves 2 things. One is the change of the linear polarization. So initial linear polarization direction may be tilted. That is parameterized by this core angle. And another experimental information is the change of a linear polarization to this elliptic polarization. So that is parameterized by ellipticity parameter, epsilon k. And both of these parameters are proportional to anomalous Hall conductivity at optical frequency. That is the frequency of laser used to probe this magnetization. And we know that anomalous Hall conductivity depends on amount of magnetic moment. But in case of a spin moment induced anomalous Hall conductivity, spin-orbit coupling is mandatory. But in case of orbital angular momentum induced anomalous Hall conductivity, spin-orbit coupling is not really required. So if we have a very weak spin-orbit coupling, then it is expected that MOG, the core angle or ellipticity per orbital moment is much larger than the core angle or ellipticity per spin magnetization. So I may say that MOG is more sensitive to orbital moment rather than spin moment in weak spin-orbit coupling material. So this is a very good experimental tool to probe the orbital moment. So this is our calculation. So here, this blue bars represent theta k and epsilon k calculated for orbital moment. Here we simply assume that the magnetization is uniform and calculated resulting core angle and ellipticity. Whereas this orange symbol or down symbols represent the result from spin multiplied by factor 50. So we see that again, this orbital response is much larger for titanium. At the photon frequency, photon energy of 1.58 electron volt used in Professor Jung-Min Chek will present his result right next to me. And there is still another method. So here, the experiment basically probed 2 quantities, core angle and also ellipticity, and they will have a relative phase. If I combine them, I will have a complex number with certain well-defined phase angle. And this phase angle affects experiment. So here I plotted core angle represented by black symbol and ellipticity as a function of titanium thickness. And you can see that the response is not just simple monotonic function. They depend on thickness. For instance, they may change sign like this, like half oscillation. And this thickness dependence profile is very sensitive to their relative, the phase angle of this theta k, complex theta k. And we can calculate, both this and this for orbital and spin. And so we can calculate phase angle of a complex core angle. And so from this, we can extract a complex phase angle of orbital and spin. And we may compare that calculation result with the fitting result. So fitting of this experimental result, determines the phase angle of this, complex core angle. So when we compared a fitted result with the calculated result, we found that the agreement with the orbital part is excellent, whereas the spin part has a very different phase angle. So this shape provides another knob to distinguish orbital response from spin response. So, okay, so by the way, more details will be given by next speaker, and one of my students will discuss details of this calculation. And so I've presented some merits of this measurement, but there is also a demerit. In case of orbital torque, all I need is orbital Hall conductivity. But in case of orbital accumulation measurement, what is the amount of orbital accumulation is not entirely fixed or determined by orbital Hall conductivity, but instead is product with the orbital relaxation length. And this the orbital relaxation length, on the other hand, spin response, spin accumulation will be given by spin conductivity times spin relaxation time. Now here, conductivity is much larger for orbital response, but for relaxation time, the spin has a much larger relaxation time because here spin-orbit coupling is very weak. Whereas the orbital relaxation time, it is suppressed by the crystal field. So this crystal field partly reduces the margin between orbital response and spin response. But nevertheless, so if I combine all these merits and demerits, we found that the orbital local signal from orbital mode accumulation is still much larger than the spin accumulation signal, and also orbital has a different thickness-dependent shape. So that allows us to distinguish orbital response from spin response with confidence. And final product. How much time do I have?
We have like 15 to 60 minutes.
15 to 60 minutes.
We have a couple of quick questions here.
Okay. Yeah.
Okay.
Excuse me, just for a second.
A question actually from the online part. So from Mark, so what if the has different orbitals from the non-magnetic material? Can L still be injected?
That's excellent question. Yeah, so if the okay, so suppose I have a non-magnetic and ferromagnet, and if these two have a very different orbital character, then I expect that kind of, we may consider kind of, orbital injection efficiency, and that will be pretty low.
So that,
Yeah.
I think, yeah.
It depends on how well the crystal matches, and so, also how well the orbital is converted from one side of material to different material.
One more question. This mock is a scanning mock or
I'm sorry, I didn't hear you.
the mock measurements, they are in scanning mode. How you do the mock measurements?
He's done, I believe, scanning mock measurement. So he can measure mock signal while making a scanning along, let's say, probably, let me see, along this direction. Yeah. So from the scanning information, actually, he can separate this orbital mode signal from a Western field signal, etc.
Okay. And your current was continuous?
That's, I don't know. Maybe next speaker look at it later.
That's not a short question.
Okay. So final part 3. So here I want to discuss some qualitative difference between orbital dynamics and spin dynamics. Well, we know the orbital angular momentum and spin angular momentum. They share many things common. And that makes distinction between orbital dynamics, detection of orbital dynamics from the spin dynamics difficult. But there are some properties that are qualitatively different between these two degrees of freedom. And so let me start with the crystal momentum spin coupling. So in case of spin, we know that spin can couple to crystal momentum only in non-centrosymmetric system. And how about coupling between crystal momentum and orbital angular momentum? And this may be related to the question about the Hamiltonian. What is the shape of the Hamiltonian for orbital Hall effect? So let me just imagine L may be coupled with crystal momentum in centrosymmetric system. And let me try symmetry analysis. Well, we know how orbital angular momentum transform under inversion. We know how crystal momentum transform, and we also know transformation rule for time reversal. So we may just apply this transformation rule to check any possible coupling between L and K is okay or forbidden. So let me try this bilinear coupling between orbital angular momentum and crystal momentum, and it is forbidden by inversion. And if I raise the order of a crystal momentum to second order, this coupling is forbidden by time reversal. So, okay, let me keep going on. How about cubic order? This is forbidden by inversion. Now, fourth order, this is forbidden by time reversal. So I don't find anything interesting. But what if I increase the order of orbital angular momentum, like second order orbital angular momentum coupled to linear order in crystal momentum? Now, this time situation is worse. They are forbidden by both inversion and time reversal. But if I increase the order of crystal momentum to second order coupled to second order orbital angular momentum, they are comparable with orbital angular this inversion and time reversal. So symmetry do not prohibit orbital angular momentum to be coupled to crystal momentum, although coupling requires a bit higher order. And this is not the only example. If we write down, many possible coupling with even order of L coupled to even order of K, they are all allowed, I mean symmetry-wise. So LK coupling is possible even in centrosymmetric system. Then we may wonder, how about spin momentum coupling? We know that spin momentum coupling requires inversion symmetry to be broken. But what about this kind of coupling? Spin second order, crystal momentum second order. They are compatible with both inversion and time reversal. So actually, spin momentum coupling is not forbidden by the combination of these two. They are allowed. But there is something else that forbids this coupling. So for that, let me consider this indices. So here, indice I and M, suppose they are the same. Suppose we have sigma x, or sigma y. We know that they are identical. So spin dependence disappears if these two spin indices are the same. So useless. But if these two spin indices are different, let's say sigma x, sigma y, then we have I times sigma z, that is anti-Hermitian. Or if I want to extract only Hermitian part of this, there is no Hermitian part. So symmetry-wise, this kind of SK coupling is allowed, but all allowed coupling between spin and momentum are anti-Hermitian. So to be precise, spin momentum coupling is possible even in centrosymmetric system, but they are all anti-Hermitian. Whereas orbital crystal momentum coupling, they have this kind of coupling, and they have a Hermitian part because Lx times Ly plus Ly times Lx this is Hermitian and this is non-zero in general. So LK coupling is possible. So maybe let me write down one just example. Suppose we have this kind of coupling between crystal momentum and orbital angular momentum. Second order in crystal momentum and second order in orbital angular momentum. And for this, and suppose we are dealing with p orbital system, and then we can find out the eigenstate set by this Hamiltonian, and the result is this. And this is exactly the orbital texture assumed by Dong when he write this PRL paper in 2018. And so this coupling between L and K shows that this coupling between K and L are indeed allowed, even in centrosymmetric system. Okay, let me move on. Now, next question is whether this kind of coupling is indeed possible in real material. Also here, I will suppress KG for illustration. And so I've just looked up some two-dimensional systems and graphene, which is graphene with some additional hydrogen attached. And this is a standard structure. And if the graphene is a little bit pitot, somewhere, so suppose formula level somewhere here, the Hamiltonian here is described exactly by this Hamiltonian with this, and this Hamiltonian reproduces orbital, the wave function nature of this graphene exactly. And another point that I want to address is that here, this splitting between two bands here sets the energy scale of this LK coupling, which is order of a few electron volt. So LK coupling is usually much larger than SK coupling. SK coupling is over the order of 0.1 electron volt or smaller. But LK coupling is 1 or 2 orders magnitude larger. And well, there are many more material, and depending on details of the material, this LK coupling has differentiate, and this is discussed by one of my students, Hyun-Woo, at his poster. 5 minutes. Okay. And let me skip this. And another things. Another difference between spin and orbital angular momentum. So suppose spin is the only degree of freedom, the only relevant degree of freedom, and crystal momentum. And most general Hamiltonian may be written like this. So initial spin up state, stay spin up, or spin up state flips to spin down, or the other way around. So for spin state, spin degree of freedom as Hamiltonian may be represented by 2x2 matrix. And general 2x2 matrix can be represented as a sum of Pauli matrices, 3 Pauli matrices and identity. So I may say that spin dynamics is completely described by 3 Pauli matrices or spin operator. But orbital angular momentum case, suppose I have only orbital angular momentum degree of freedom, then dynamic, the Hamiltonian is something like this. Initial LZ, let's say +1 to a final LZ -2, etc. So suppose this electron is P electron, maybe Hamiltonian, maybe written like 3x3 matrices. So 3x3 matrices have 9 independent degree of freedom, whereas for orbital angular momentum operator, we have only 3 operators. So that means orbital angular momentum operators, they do not provide complete description of orbital dynamics. We need extra degree of freedom, and this extra degree of freedom is what I call orbital angular position. So the name is similar to orbital angular momentum, and you will see that the relation between these extra terms and the first term is very similar to relation between position and moment. So for p orbital system, we can write down general Hamiltonian like this: identity plus 3 orbital angular momentum operator plus 6 orbital angular momentum position operator, which is a symmetric combination of 2 orbital angular momentum operator. So here I have 6 plus 3 plus 1, which is total of 10 terms, whereas I have 9 degree of freedom. But the thing is that if I make a certain linear combination of 6 orbital angular position operator, I will produce identity. So I may throw out this. So these two provide complete description of orbital angular momentum dynamics in P system. And so to provide complete description of orbital dynamics, we need to discuss not only orbital angular momentum dynamics, but also orbital angular momentum position dynamics. And maybe let me spend my rest of the time to look at this. So, by the way, how do they differ, orbital angular momentum and orbital angular momentum position? So suppose I have some initial orbital like this. Then orbital angular momentum implies that this orbital direction changes with time and they precess with time. So there is an angular frequency of this. On the other hand, orbital angular position operator, which is a combination of L times L. And you can just play with this operator a little bit, and you can find that their eigenstate, they simply detect which real orbital direction is pointing at, whether it is pointing along X direction or Y direction, somewhere in between. So this operator calls angular direction or angular position of orbital degree of freedom. Okay, so the chairman is forcing me, so let me say. Okay, let me skip everything. Yeah, so let me jump to summary. So I try to emphasize that electron orbital angular momentum is not necessarily quenched in solid, even without spin orbit coupling. And well, it is often said that crystal field suppresses orbital angular momentum, but Claude shows that crystal field actually sometimes suppresses, but on the same time, it can enhance orbital angular momentum in certain situations. And that is the state where orbital angular momentum dynamics becomes important. And on top of that, this orbital may be the source of many spin properties. And also sometimes the orbital properties may be qualitatively different from spin properties, although I don't have a time to discuss these details. And finally, there seems to be some experimental support about this orbital gravity orbital dynamics. So that is the end of my presentation. Okay, thank you.